Okay, welcome to the one of the last few lectures of the semester on CT509. We'll start right away. So we have talked about NOMA to some extent. I think we have covered many facets of NOMA. We have looked at the information theoretical analysis on the return link, as well as we looked at the analysis of NOMA on the forward link. And we saw that both on the return link and on the forward link, the NOMA actually outperforms the orthogonal multiple access and definitely CDMA with SUMF. And just hold on. Okay, we saw that why NOMA is motivated not only on the return link but also on the forward link. And then we saw several different research areas of NOMA. We looked at the hybrid NOMA, successive interference cancellation that is leveraged in NOMA, how it can fail. We saw how to determine the power allocation ratios, let's say on the forward link at the base station. We briefly considered the multi-user MIMO with NOMA, and we saw how there can be some intra-group NOMA in conjunction with intergroup MIMO precoding or MIMO cancellation, interference cancellation techniques. Cooperation among the users is facilitated with the use of NOMA. We saw that, and then we also looked at the potential applicability of NOMA with millimeter wave communications in 5G. Then the last topic is on the NOMA algorithms, specifically the successive interference cancellation type of algorithms. And we saw that there are multiple different techniques. The low densities spreading type of NOMA, the sparse code multiple access NOMA, multi-user shared access NOMA, and so on. So I'm not going to go into all of them in a lot of details, but I'll very quickly show you one particular paper. I'll be posting this paper on our Google Classroom, which shows two techniques. One is SCMA and another is LDS SCDMA, the low density spreading CDMA. And I just want to show to you the structure of these techniques. So on this page of this paper, this is a paper written in 2015 by Ling Long Dai. This appeared in IEEE Communication magazine. And it is a fairly comprehensive paper. It talks about not only the transceiver algorithms, but also some of the research domains of NOMA that we just now talked about. But let us focus our attention on this LDS scheme. So this is actually just a CDMS scheme where each user is transmitting some data, and that data is being spread using a spreading sequence. Very much like what you have done in the lab 4 of CT509. So there you would have a spreading sequence with 8 chips per symbol, right? Those instead of those 8 chips here in this LDS CDMA, they are using 4 chips. So this Y1 to Y4 are chips. So this each symbol is getting spreaded over 4 chips. Now, in your study of Lab 4, you would have multiple users, and they will be using different signature sequences, and those signature sequences superimposed on each other. So likewise here also, this user 1 is transmitting some symbol x1, but that x1 is getting spread using this signature sequence with 4 chips. Similarly, user 2 is transmitting a symbol x2, and it is also getting spread over the same 4 chips. But the unique aspect of low density spreading is that if you look at user 1, his signature sequence is 1100. You see that the symbol is getting, the signature sequence is 0 for Y3 and Y4. That is why X1 never appears on the chip number 3 and 4. Similarly, X2 is getting spread only over Y1 and Y3. And now there is no presence of the second user on chip number 2 and chip number 4, and so on. So this is a kind of a graphical representation of how different users' signature sequences look like. And one departure from what you have done in Lab 4 is that the signature sequences can take values of 1s and -1, but they additionally can take values of 0. So user 1 signature sequence, for example, could be 1, -1, 0, 0. User 2 could be -1, 0, -1, 0. So 1s and -1 would be random, but the point is that there are some chips which are never getting utilized by different users. And if I consider more number of users, then the idea is that the signature sequence will be mostly filled with zeros for a particular user. Only at a few chips, the user will be spreading its symbols. Okay, so that is the main idea. That is why the name low density spreading comes into play. The claim is that now, if I look at a particular chip, it will have interference only from a few users, not all of them. And therefore, I may be able to extract individual chips in a more effective manner. And that is what this diagram illustrates, that with only 4 chips, they are able to multiplex 6 users, which means 150% overloading. In your Lab 4, you would have seen that if you start approaching anywhere close to 100% loading, then the performance deteriorates for most of the interference cancellation schemes. I mean, for SUMF, you just forget about it. You can't approach anywhere close to 100% for SUMF. But even for the other schemes, close to 100% loading means you are dealing with a lot of interference, and even the decorrelator may not work very well. Even MMSE may not work very well. Whereas here, even with 150% overloading, the claim is that this scheme will work pretty well. A similar idea is there, which is called SCMA, sparse code multiple access. And that there also, if I look at different transmissions, they have some predefined code books. So if a user has to transmit 00, then the user will randomly pick one of these 4 code words. And you will see this code word has zeros in the last 2 positions. Any one of these 4 code words in this code book have zeros in the last 2 positions. And so on, 1 0 0 1 1 1 and so on. They have some predefined code books. One of the 4 members of this code book is picked on random, and then it is getting transmitted. So again, here the idea behind this sparse code multiple access is similar to the LDS CDMA, and one can actually formulate this type of graphical structure even for SCMA. Okay, so a lot of this NOMA techniques, if not all of them, I would say many of them, the way they actually make use of channel coding is by leveraging some of the ideas of this type of graphical structures that we were just looking at. Okay, so now with that as our backdrop, let us now move on to a new topic of LDPC codes. Okay. I wish I had planned to cover this topic in CT516 only, but we ran out of time that time. So we will look at this LDPC code today, and maybe maybe we'll need one more lecture. But the point that I wish to convey to you is that the technique of this LDPC code, the decoding of LDPC code, is based on this message passing technique. And this message passing is happening on a graphical structure which is similar to the graph that we just now were looking at for LDS-CDMA. Okay, so in order for us to fully appreciate the decoding algorithms for NOMA, I think it is necessary that we fully understand the message passing structure. And by the way, this message passing has become very powerful these days. It is being applied for compressive sensing, for example, and a host of other signal processing as well as machine learning techniques. Okay, so let us just do a brief review of the different channel types that we have looked at in CT516. One is called binary symmetric channel, which with some probability P flips the transmitted bit. So 0 can become 1 and 1 can become 0. And that probability P is the same, whether it is 0 which is transmitted or 1 which is transmitted. And that is why it is called a symmetric channel. Binary because we are dealing only with zeros and ones. Okay, there is another channel that we have, I think, also looked at in CT516. It is called binary eraser channel. And here, either the bits are being received successfully, that happens with the probability of 1 minus P, or they get erased, and that happens with probability of P. Okay, so those are the two channels that we'll be looking at. We have covered some of the basic channel coding schemes. One is called single parity check code. And the idea is very simple. You take some number of bits at the input, and then you add one bit, extra bit, it is called the parity bit, And the objective of adding this parity bit is that, including the parity bit, the entire code word should have even number of ones. And so suppose if you have n equal to, let us say, 4, then your code word length will be 4. Code word will have 4 bits. But your message bits will be only 3, M1, M2, and M3. The way you encode these 3 bits is you just do a modulo 2 sum. And that sum will be 0 if these 3 bits have even number of ones, and otherwise it will be 1. And so now if I look at all the 4 bits, they are guaranteed to have even number of ones. Okay, so that is the idea of SPC code. And this is a way by which we can represent the SPC structure on a graph. And the reason I'm doing that is because, as we just said, for the NOMA and more generally for the message passing structures, we will be making use of the graphical connections. So this SPC code can be put on a graph. What this graph is showing is that there are 4 bits of the code word, C1 to C4, where the first 3 bits are connected to the message bits, and the 4th bit is connected to the parity bit. And then there is a supervisory node, which also is actually a bit only. This S1 is actually a bit. And at the transmitter, what transmitter says is that I will make this supervisory bit S1 to be 0. And in order for S1 to be 0, I will play around with P1. After I get the 3 message bits, which can be arbitrary, there can be 7 possibilities, 8 possibilities of these 3 message bits. I will look at a particular sequence of the 3 bits that I got, and then I will make P1 to be either 0 or 1 so that S1 is always 0. What these connections are showing is that at S1 we are taking all these 4 bits and adding them up, modulo 2. Okay, so that is the idea behind the SPC code. So we can consider the decoding of SPC code, specifically what is the methodology. Well, at the receiver, we will take this n bits, in this case 4 bits as the input, and we'll just compute the modulo 2 sum of these bits. Sorry, there is a typo here. And if this sum is 0, basically at the receiver we will make, we'll calculate this S1. If S1 is 0, we will be satisfied. We'll say that, okay, what we got is most likely going to be correct. But unlike at the transmitter where S1 is forced by the transmitter to be 0, at the receiver, because of the errors that can happen, and here we are specifically considering binary symmetric channel, zeros can turn into ones and ones can turn into zeros. If one error has happened in the transmitted bit, then the received sequence of 4 bits, instead of having even number of ones, it will have odd number of ones. And so this S1 supervisory node, also known as check node, because it is checking the parity among these 4 bits. So this check node will be equal to 1. Now it will take a value of 1. So whenever it takes a value of 1, we right away can say that something has, some error has happened. And we may not be able to correct it, but at least we will be able to identify that and an error has happened. Modulo 2 sum here is nothing but XOR operation. That is correct. So this can be implemented using some logical gate, XOR gate. In general, although we will be just looking at it as some type of summation here. Okay, so this particular decoder is very, very simple. All you do is take these 4 bits, add them up, and if that added value is 0, then you are happy. You say that the bits received are without error. If the added bits have the answer is 1, then you say that some error has happened. Now, it can be that 2 bits are in error, or 4 bits have been flipped, or 6 bits have been flipped. When some even number of bits have been flipped, when you add the bits up, you may still end up getting S1 to be 0. Right? It is not very difficult to come up with an example. Suppose the transmitted code word is 1010, right? It is even number of ones, 2 ones. And let us say that the first 2 bits are in error. So the received sequence of bits became 0110. So receiver will think that there are no errors because the 4 bits have even number of ones. But actually 2 bits have become flipped. So what is said about the SPC code, especially the hard decision decoder, is that it can detect up to 1 bit of error. What means up to 1 bit? Means that it can, 0 bit is always fine. But if 1 and only 1 bit is in error, it will be able to detect it. But if 2 bits are in error, it may or may not be able to detect it. If those 2 bits if the 2 bits are corrupted, then the SPC code will be happy. The supervisory code will be, the supervisory bit S1 will be 0. Again, if 3 bits are in error, it will be able to detect it, but it may not be able to say that 3 bits are in error. It may still think that only 1 bit is in error. And so the SPC code can detect at the most 1 bit of error. Beyond that, it kind of becomes blind. And secondly, it is also blind in the sense that it doesn't know where this error happened. Only thing it says is that some bit is in error, but which bit is in error? No idea. Okay, so that is the idea behind the decoder of SPC code, and this is called hard decision decoding because the receiver is operating on zeros and ones. Okay, now there is something called soft decision decoding, and that is applicable when the receiver knows the probability of zeros and ones that it is getting. So what do I mean by that is that let us say that this, again, take an example of this 4-bit code word, SPC code word. It got transmitted and the transmitter, let us say, use BPSK modulation. So zeros got mapped to minus 1 volt and ones got mapped to plus 1 volt, let us say. And then at the receiver, the transmitted BPSK symbols arrived with additive Gaussian noise. Now, at the receiver, if the receiver saw some values which are very high positive voltages, then it knows with a very high probability that the incoming bit or incoming symbol must have been 1. If it saw voltages which are very low negative, -1 or -2 or some voltages like that, then it also knows with very high probability that most likely the transmitted BPSK symbol was -1. But if it sees voltages which are around 0, then it doesn't know very definitively whether 1 or 0 was transmitted, because the received voltage is now falling close to the decision boundary, which is 0 voltage for BPSK. So the BPSK modulator, in addition to giving to the decoder the hard decisions, whether each BPSK symbol corresponds to bit 1 or bit 0, it can also give the probability of whether the transmitted bit was 1 or whether it was 0. That probability it can form using the Bayesian math. The posterior probability of the transmitted bit given the received voltage is what it would calculate. And that type of calculation we have done in CT516. And so by doing such calculation, the receiver will be able to pass to the channel decoder not only the hard decisions about the transmitted symbols, zeros and ones, but also the probability of the transmitted bit being 0 or the transmitted bit being 1. So let us consider again the same length 4 SPC code, and let P of n denote the probability that the nth coded bit is 1. This is the probability that the demodulator has given to the decoder. Okay? Now, this is a question that I ask of you, that suppose the receiver has knowledge of P1, P2, and P3 only. Let us take that as a statement of the question. The receiver knows P1, P2, and P3 somehow. Can it determine P4? Now, I'll give you a high-level answer first of all, and then I'll ask you if you can give me more detailed mathematical reasoning behind this answer. So the high-level answer I will give you is that, remember, this is the SPC code, right? And so if I look at the first 3 bits and at the decoder, if I am told that the probability that the first bit is 1 is very high, P1 is almost 1, P2 is also very high, let's say it's also 0.99, and P3 is also pretty high, maybe 0.98. So at the receiver, I know that the first 3 bits are most likely going to be 1. Then what would I say the value of P4 would be?
1.
Yeah, I would say that P4 is most likely going to be very close to 1 also. Because when the first 3 bits are 1, then the 4th bit has to be 1 also. On the other hand, suppose P1 is pretty close to 1, P2 is pretty close to 0, and P3 is pretty close to 1. Then I will make P4 close to 0 instead of 1. Does that make sense?
Yes, sir.
So now my question is, what will be a way that you can determine P4 mathematically? This is a high-level answer I gave you. How would you be able to determine P4 mathematically? And to answer that question, this is the table that you may consider. These are all the 4 possible ways that this 4-bit code word can be received. There can be 16 different ways of receiving this 4-bit code word. The question is that when you are giving the probability of the first 3 bits, C1, C2, C3, how would you determine the probability of C4 being 1?
So based on summation, we can predict P4. I mean, if P1, P2, P3, in case of an odd parity, we can keep it as like if P1 plus P2 plus P3 is somewhere close to either 1 or 3, then we can make P4 as 1. And in the rest of the case, if it is either close to 0 or 2, we can make P4 as 0 to determine it. Hello.
Yeah. Okay, Bhavesh, I think it's a good thought. But there is some little bit of ad hoc math there. I mean, that's a good start, but I would say that there is actually more definite way of calculating this P4.
Sir, we can consider a conditional event like probability of P4 equals to 1 P1 P1 P2 P3 and use Bayes theorem.
Yeah, that is the way to proceed. But how will you do that?
Each event is independent event, no, sir?
Correct.
So probability of P4 equals to 1 given P1 P2 P3 will be probability of P4 equals to 1 intersection P1 P2 P3 given, I mean divided by probability of P1 P2 P3.
Yes. Assume that all these 16 events are equiprobable. Okay. So here we are asked about the probability of C4. So C4 column, let us kind of put a square, a rectangle on it. Okay, so let's hide C4 column. Let's not look at C4 right now, because C4 is now the variable that we are asked to determine. C4 is almost a dependent variable. Similar to, I think, what Anudeep was saying, the probability of C4 is going to get determined based on one of these events. And these events are independent. Now, which are the events in which C4 is equal to 1? You will see that C4 is equal to 1 in event 9, 10, 11, 12, 13, 14, 15, 16. The last 8 events are the ones in which C4 is equal to 1.
But
right?
they are repeated events, right?
Sorry?
The first state and the last state are same only. I mean, for one, it's just repeated event, right?
Okay, so let us.
So based on this table, it is just 1/2, like the probability of C.
Right. No. So sorry. Yeah. I think Joel, you are right. Based on, if I look at all 16 events, it is 1/2. Yeah. Sorry. So I think I drew this table
Reversed.
impartially, not completely. What I should have done is row number 2, 3, 5, 8, 9, and so on. Half of the rows I should have blanked out. Okay, I think I should have this table with me. Just bear with me. No, not really. Actually, I deleted the row table, but it fine. So let us see how to do this. Okay, so for the sake of simplicity, I'm now going to consider only 3-bit code word instead of 4-bit code word. So this will okay. So this is the now because this is the SPC code, I will happily delete. This is my parity check bit. Sorry, my supervisory bit. Right here is where I'm doing the summation. And so I will delete the rows where the sum is 1 because these are invalid code words. So as expected, I'm left with 4 possibilities. Okay. So I don't need this anymore. I'll get rid of it. So the question is that we are given the probability of C1 and C2 in this case, and we are asked to determine the probability of C3. And now, actually, there are only 4 events. The question is, and yes, now these 4 events are independent. Let us assume that they are equiprobable. The question is, how would you determine the probability that C3 is equal to 1? In this case, the probability that C3 is equal to 1 will not necessarily be just 0.5. It will depend on the probability of C1 and C2. So, by the way, you are able to see my screen, right? This Excel you are able to see?
Yes, sir.
Okay, so let us consider the events in which C3 is equal to 1. So it's obviously these two events. These are the events in which C3 is 1. And C3 is our dependent variable. So in order for us to determine the probability that C3 is equal to 1, because this event 3 and event 4 are independent, first of all. And secondly, when C3 is dependent, how can I determine the overall probability that C3 is equal to 1? Here, let me ask you this. What is the probability of event 3? We'll assume that C1 and C2 are independent of each other.
1/4.
Sorry?
So P1 into 1 minus P2.
1.
Correct. P1 into 1 minus P2. Right? It won't be 1 over 4 because C1 and C2 have different probabilities of being 1. So this will be P1 into 1 minus P2. What will be the probability of this? It will be 1 minus P1 into P2, similar to what Anudeep just now said. So the question is, what is the probability that C3 is equal to 1?
Addition of these two.
Addition of the two. So P1 times 1 minus P2 plus 1 minus P1 times P2. So that is how you can determine the probability that C3 is equal to 1. So that is one of the main ideas behind the message passing. Message passing, as the name may look fancy to you, but the idea is that this individual nodes here, they are getting their probabilities from initially they are getting their probabilities from the demodulator. And what they do is they pass their probabilities to the supervisor node. And what supervisor will say is that, okay, it will tell the first node here, C1 node, that you know what, I got the three probabilities of 0.9, 0.99 and 0.01 from your three neighbors. And so because I got those values from your three neighbors, the probability that you are 1 is pretty small. I will tell that your probability, the probability that you are 1 is only 0.05. And so if suppose the receiver got confused for some reason and it told the first bit that its probability of 1 was like 0.6 or something, this message passing will possibly correct the probabilities that this bit had. So the idea behind message passing is the message should be actually called probabilities, or actually they are beliefs in some sense. Belief regarding whether a particular node is 1 or 0. So message passing scheme is also called belief passing scheme or belief propagation scheme. So each of this node is sending its belief regarding whether it is 1 or 0 to the supervisory node. And then supervisory node takes 3 out of these 4 nodes, and then using that, it tells the remaining node what its probability should be. So messages are going from the node, bit node upward to the supervisory node, and then supervisory node sends a message back to one of the remaining bit nodes here. So that kind of is an overview of the message passing. And we saw how in the case of a 3-bit code word, how the supervisory node can take messages from bit C1 and C2, and using those 2 messages, how it can inform C3 about what its probability of being 1 is equal to. In this case, as we saw, it is just P1 times 1 minus P2 plus 1 minus P1 times P2. When we consider, instead of 3-bit code word, if we consider 4-bit code word, then we will have to pick the 8 rows of this table, which correspond to even number of ones. And then we would essentially apply the same type of idea. Here we did it only over 2 bits. And so our answer was P1 times 1 minus P2. When we have 4-bit code word, we will have 3 such values. P1 times 1 minus P2 times P3 or something like that. So that is how the probabilities of this 4th bit can be calculated. By the way, there is nothing special about the 4th bit. If the supervisory node can take probability coming, the belief message coming from C1, C2, and C4, and it will tell C3 what its probability of 1 is going to be. And same thing it can repeat for C2 and C1. The main idea is that how do you take 3 out of 4 probabilities for the SPC code, and using that, how can you tell the remaining bit what its probability is going to be. So we did this calculation for a case of 3-bit code word, and there the answer was simple. Now you can go from 3-bit to 4-bit, 4-bit to 5-bit, and see what is going on, how the formulas are turning out to be. And if you spend enough time on it, and if you are pretty good, very mathematically very competent, like Robert Gallagher is, you will come up with a general formula like this. And this formula works for any value of n. And it doesn't matter which bits we are talking about. What this says is that if I am given an n-bit SPC code, and if I am told the probability of some n-1 bits, P of I, then using this formula, I can calculate the probability that the remaining bit is equal to 1. So we are not going to derive this formula here. This Gallagher's paper on LDPC code is a very famous paper. If you just do a web search on Gallagher original paper on LDPC code, you will find that paper available online. And in that paper, you will see that there is a proof of where this formula is coming from. If you read the proof, you may not understand it. But if you are mathematically inclined and if you try to derive this formula on your own, using the method that we just now looked at for 3-bit code word and go to 4th bit, go to 5-bit and see what is happening, what is the common logic, then maybe you yourself may be able to derive this formula. Anyways, the derivation is kind of a sidetrack. The main point is that this type of calculation is possible at this supervisory node. Okay. Now let us move forward. We will look at another code which is called repetition code. I don't know whether we looked at repetition code in CT516 or not. Can you remind me, did we look at repetition code in CT516 by any chance? Have you heard of repetition code before?
Yes, sir, we did study.
Yes, sir.
Okay. So then this part, at least the first few slides will be pretty straightforward. Essentially, we are just repeating one bit at a time, but we are repeating it n times. So this is the diagram. Let us say the information bit sequence is 011 101. And we are using rate 1/3 repetition code. So each 0 gets repeated 3 times, 1 gets repeated 3 times, and so on. Then after it goes through the BSC, maybe some zeros become 1 and 1 becomes 0, as it is indicated in the red. If you have done this repetition code in CT516, you would know that the decoding strategy is just the majority voting. We take 3 bits at a time, and in this case, the majority is zeros. So we will decode this code word as 0. The second code word, the majority is 1. So we'll decode it as 1, and so on. Now this again is hard decision decoding because we are acting on just zeros and ones. Whenever we have soft information, and soft information means those probabilities P of n, it is always better. Why it is better is because you see that if I knew that the probability of this 1 here in red, the probability that this third coded bit is 1 is very, very small, right? I mean, it's, when I say very small, I mean compared to the decision boundary. So if I say that this 1 has a probability of 0.51, then I actually can be more or less certain that it's most likely 0 which got flipped into 1. Okay. So so knowing the probability of this individual bits is going to be helping me. The other case is, let us say that if I know the probability that these first 2 bits are 0 is pretty high. Let's say this 0 is, the probability is 0.98 and this 0 probability is 0.91. Then I don't even have to look at this third bit. I can say that most likely the transmitted bit must have been 0, because only then these first two bits will have very high probability of turning up as zeros. So basically the probabilities of this individual encoded bits is highly informative. It tells you a lot about what the actual bit sequence could have been. Sorry, just hold on. Okay, so sorry for the interrupt. So anyhow, for the repetition code, just as we saw for the SPC code, having this probability information is always useful. The decoder can do a potentially better job of figuring out whether the transmitted bit is 0 or 1. So I will ask you the same question again. That suppose if we have the information available to use soft decision decoding, basically the same P of n value is available, where P of n indicates the probability that nth bit is 1, then also I'll go back to the same question. Let us say it is a 4-bit repetition code, and you are given P1, P2, P3. How will you determine P4? I'll give you one hint. The answer is pretty straightforward. We don't have to be concerned about this complicated looking math formula anymore.
Sir, there will be 3 cases. Like P1, P2, 1 minus P3, P1, 1 minus P2, P3, 1 minus P1, P2, P3. Because the number of ones have to be even.
No, for repetition code.
For repetition, okay.
Yeah, I'm talking about repetition code. You can take a look at this table here. And first of all, what you would have to do to this table to make it repetition code table? Which events you will have to kind of delete? The transmitter can be only in one of the 2 events. Which are the 2 events for the repetition code?
So the first and last.
Yeah, exactly. First and 16th. So given that now that we have pruned our events table to just event 1 and event 16, now can you say the answer to this question?
Sir, P1, P2, P3.
Exactly. So the answer is that actually the answer is pretty simple. All we have to do is just take the product of the probabilities. Oh, by the way, there is a typing mistake here. This would not be equal to sign. It would be proportional to sign, because actually we have to use Bayesian math to determine this P of n. And when we do Bayesian math, this will give us just the likelihood function. But that likelihood function will have to be scaled by the prior divided by the evidence. And that scaling will give us some multiplier term alpha, which is common for the probability that nth bit is 0 as well as nth bit is equal to 1. And value of alpha is that without the alpha, if I do the summation of P of n and 1 minus P of n, it will not be equal to 1. That alpha multiplier will make sure that this P of n is such that the sum of the probability that the bit is 1 and the probability that bit is 0, that sum is always going to be equal to 1. So anyways, so the point is that similar to what we saw for the SPC code, even for the repetition code, we can determine this probability. If you know the probability of n minus 1, some n minus 1 bits, we can determine the probability of the nth bit. Okay, I haven't written this down. Maybe I should have added one more slide. In a lot of the message passing schemes, to avoid this alpha complication, I mean, it's not complication, but it's additional detail. What the message passing does is it, instead of passing P of n values, the values that are passed are P of n divided by 1 minus P of n. So probability that this bit is 1 divided by the probability that the bit is 0. Now that is called, do you know what it is called? There is a term for P of n divided by 1 minus P of n.
Odds in favor.
Yeah. Oh. Yeah, fine. I'll take that answer. But in the literature, you will find the term likelihood ratio. So instead of transmitting probability messages in the message passing algorithm, what are being transmitted are the likelihood ratios. And one is recoverable from the other. If you have likelihood ratios, you can calculate probabilities. Or if you have probabilities, you can calculate likelihood ratios. The reason likelihood ratios are favored is because you don't have to worry about scalar multiplier alpha, which makes sure that the sum of probabilities is 1. In likelihood ratio, that alpha is a common term, so it cancels out. And actually, it turns out that instead of even likelihood ratio, if you take logarithm of likelihood ratio, then this products becomes just the summation. And it's sometimes easier to work with sums instead of products. And so purely again because of the computational reasons, in the literature of message passing, you might see that the message contains the log likelihood ratio or LLR instead of just the likelihood ratio. But that part is probably a detail. If suppose you are investigating some NOMA algorithm, then I think it is completely okay if you just work with probabilities. Because while developing or understanding the concept of the algorithm, you don't want to be worried about how to make the algorithm computationally simpler or computationally friendly. So probabilities, likelihood ratios, log likelihood ratios are all equivalent to each other. They don't change the underlying concept because of which the message passing scheme works. But they help in reducing the computational cost of the algorithm. And so that is where some of the math in the literature is. And sometimes log likelihood ratios are computationally friendly, but concept-wise, they are maybe a little more difficult to understand. So if you go back to probabilities, that may allow you a simpler picture. Okay, so that is the main concept about message passing that I would wish to cover. Let's see. Okay. Now, next few slides I'm going to very quickly flip over, because I think we should have done this in CT516 also. That in the coding schemes, whether it is SPC code, repetition code, or even the Hamming code, Gole codes, Reed-Solomon, BCH, and now coming to even the LDPC codes. It helps if we start thinking of information vectors and encoded information bits and encoded bits as vectors. And so there is a vector M of information bits and vector C of message bits. And we'll denote small k as the number of information bits, small n as the number of encoded bits, and the ratio k divided by n is the rate of code. And then there is something called generator matrix, which is an n cross k matrix. It converts this k bit information bit vector to an n bit encoded bit vector. And similarly, at the receiver, there is something called a parity check matrix. And if you take H times C, then you are guaranteed to get zeros. That is the definition of the channel coding scheme. Okay, so let us take an example for the SPC code. The parity check matrix is nothing but a row vector of all ones. So in case of a length 4 SPC code, this H will be a row vector of 4 ones. C is a column vector of 4 bits. And this supervisory node, which is that S1 bit that we were looking at the transmitter side, it is always guaranteed that if you do H times C, because H is all ones, all that you are doing is just adding up the bit C. And that answer you will always get 0. That is what is meant by the parity check matrix. The generator matrix can be actually derived from the parity check matrix. And in case of the SPC code, and in general for any other code, what will happen is the generator matrix will have the first part, which is an identity matrix of size k, and the bottom part, which will be dependent on this H. So in case of SPC code, it will be an identity matrix of k, and then the last part of generator matrix will be just this H vector. So what this generator matrix will do is, when you, so by the way, generator matrix for the length 4 SPC code will have a size of 4 cross 3. This identity matrix will be 3 cross 3 matrix. And so when you put some 3 bits as the input, what will come out is first 3 bits will always be the same 3 bits that you fed as the input because of this I matrix. And then the last bit will be modulo 2 sum of those 3 bits. Okay, so this is just an example for the SPC code. For the repetition code, it turns out that G kind of becomes H and H becomes G. And that is why sometimes SPC and repetition codes are called kind of the dual of each other. So let us not spend too much time on this G and H matrices, but remember that they are linear algebraic representation of these channel codes. Let us take a look at one specific type of code, which is known as product code. Did we do product code in CT516 by any chance?
No, sir.
Okay. So then this may be new for at least some of you. The reason why this code is called product code, maybe we'll come to see pretty soon, but maybe it should also be called a square code. because the requirement is that the number of information bits is always a square number. And the number of encoded bits is also a square number, which is given like this. And what is the encoding methods? What we do is we take the information bits and make them into a square array. And then we encode each row with an SPC code and each column also with an SPC code. So here is an example for rate 4/9, k equal to 4, n equal to 9 product code. So we have 4 message bits, M1, M2, 3, M4. So we put them in this square. And then we make an outer square around it by adding parity to each row and each column. So this is called the product code. And you will see that this product code is actually nothing but 5 different SPC codes sitting on the same 4 message bits. These product codes don't have to be square, they can be rectangular codes also. And for the rectangular codes, it could be that you have, let us say, 6 message bits and you turn them into a rectangle, M1, M2, M3, M4, M5, M6. The idea remains the same. Then you will encode each row and each column using an SPC code. Hemming code is also sort of like that. It is also 3 different SPC codes stacked on the same 4 message bits. And the formulation of the supervisory bits is given by these 3 equations. So this SPC code, the supervisor 1, is the supervisor of C1, C2, C3, and C5. The second supervisory code, supervisory node is a supervisor of C1, C3, C4, and C6. And then the third supervisory code is C2, C3, C4, and C7. So now we are kind of getting a graphical structure similar to what we were looking at in the context of low density spreading CDMA, right? And we have seen very briefly what type of message passing can happen, at least S1, how it can pass messages. Using that equation that is in Gallagher's paper. And same equation S2 can use, same equation S3 can use. We also looked at repetition code. And we saw how the message passing can happen from the perspective of repetition code. So one interesting insight about this Hemming code, and by the way, this type of graphical structure I can very easily draw for this code also, and we will do that very shortly. One interesting insight about the Hemming code or the product code, and eventually even for the LDPC code, is that S1, S2, S3 are obviously the single parity check code, because that is how we are defining them. What is maybe not very obvious at the first sight, but if you think about it, it will become clear to you, is that suppose if I am sitting at this circle node instead of square node, then from this perspective of circle nodes, these bits S1, S2, S3 are repetition codes. Okay, why is that? Because this first bit is connected in this case to S1 and S2. Here, M1 is connected to S1 and S2. You can see it from these two equations. And it is the same exact M1 which is getting connected to S1 and S2. So therefore, from the perspective of M1 and from the perspective of M1, this S1 and S2 become repetition code. It is the same M1 which is being replicated 2 times. This may take some time for you to absorb, but the idea is that once we put down the coding mechanism in this type of graphical structure, these nodes become SPC codes and these nodes become repetition codes. And so over here we will use Gallagher's equation. Over here we will use what Anudip asked us to do, which is just product of probabilities. That is how we will be exchanging the messages. Okay, now maybe let's continue for another few more, maybe 10 minutes or so. So what we have done is looked at how the messages can be passed from one node to the other. So it gives us kind of a very localized perspective. What is the global picture? How the actual algorithm works? So that is what we will be looking at. And that message passing algorithm or belief propagation algorithm is an iterative algorithm. In fact, it got realized by multiple different inventors. Gallagher is credited as being the original inventor of this belief propagation algorithm. But maybe 20 years later, this mathematician called Judah Pearl also developed this Bayesian belief propagation algorithm. But the work that Judah Pearl did was in the computer science community. And so his work got absorbed in the machine learning topics. But still, the idea is the same. Okay, I think I'll take a moment here to kind of go on a sidetrack, which is a little bit of a tragic thing. I mean, not little bit, I think it's very tragic. Some years ago, I don't remember how many years back, maybe more than 10 at least, there was a big news story. If you all were pretty young that time, maybe in your middle school and so on. But if you were following the news, you would have seen that some American journalist got kidnapped in Pakistan, okay, by some Taliban or some extremist terrorist group. And it became a big news story, and then eventually the poor fellow got beheaded. So the outcome was extremely tragic. And that became worldwide news. In American news media, this was like the front page story for a long time. Not only when the journalist got kidnapped, but the government was probably negotiating with the terrorist group to secure his release, and eventually those negotiations didn't bear any fruit, and that is when the terrorist beheaded the journalist. So it went on over quite some time. I knew about that, but then it was only later on that, and then I also was reading this a very nice textbook written by Judah Pearl on Bayesian belief propagation. And the name of the journalist, the last name was Pearl. And I never connected the two. It was only later somehow I came to know that the journalist, the unlucky journalist who met his tragic end, he is the son of this mathematician. So I think now if you just look up Judah Pearl on web search, and if you go to his webpage, I think you will see not only his technical work on these Bayesian algorithms, but I think he has become an activist in terms of how to deal with all this terrorist organization and so on. Anyhow, so I thought a human story in the middle of some math topics. Okay, so in context of machine learning, this iterative belief propagation algorithms are also motivated. For example, this particular paragraph has a lot of errors, spelling errors. But if you focus on this writing, you'll be able to read it, right? If you try to read this, it is not very hard to make out what it says, according to a research at Cambridge University and so on. And there is some theory that the reason why you are able to read this paragraph is because you are not looking at individual word at a time. These different letters of a word and maybe even different words together, they make some type of graph similar to the graph of Hamming code that we were looking at. And maybe some type of belief propagation is happening in our brains. So now let us move forward with the same 9x4 product code example. We'll take one specific case that the 4 message bits are 1, 0, 1, 1. And so that is how the transmitted sequence looks like. You know, we'll obviously transmit it in a sequential manner, but if you put it in a square array, this is how the encoded bits come out to be. So we'll now transmit this code word over a binary eraser channel, and we'll make this eraser channel to be pretty severe. So it will erase 5 different bits. Out of 9, 5 bits will get erased. You know, you will think that that is too much. But what we'll see is the magic of this iterative algorithm. These 5 bits have been erased, and the receiver can see only these 4 bits. So we're going to look at an iterative algorithm. It won't look like any type of belief propagation or anything, but it will kind of still help us arrive at a global perspective of this message passing structure. And so this iterative algorithm is very, very simple, very straightforward. Maybe even a high schooler can understand it. Okay, so all that we are going to do is apply the hard decision SPC decoding. Okay, and the way we are going to apply those hard decision SPC decodings are sequentially, row by row and then column by column. Okay, so we'll start with this received code and we'll go row by row first. First row, when we look at the first row, we can't do much because 2 bits have been erased. And so SPC fails in this case. Then we'll go to the second row. Here SPC will be successful. What do you think SPC will do for the second row?
1. It will change the second element will be 1.
Second will be 1. third row, will it do anything?
No, sir.
No. So after row by row iteration, we were able to unerase one bit. But the idea is that this unerasing process suddenly kind of meets kind of an avalanche or kind of a big flow. So initially you may be able to unerase only few bits, but then suddenly as more and more number of bits get unerased, you may be able to unerase even more number of bits. So now we will do column by column iteration. When you look at first column, what will you do?
That element will be 1, the first element.
1. Second column, you won't be able to work with it because there are 2 erasers.
Yes.
Third will be 1 also. So now you unerased 2 more bits. And so now you can see where we are going. You will now, this is the end of first iteration. You'll go to the second iteration. Again, start row by row. At the first iteration, first row, you couldn't do anything. But in the second iteration, you will replace this question with 0. And you will replace this question also with an unerased bit, which is going to be 1. So at the end of second iteration, not even the full second iteration, just the row portion of the second iteration, you unerased all of the bits, which is pretty impressive. So this is the global structure of the message passing algorithm, or the main idea, main concept. Now let us put this message passing in a little more formal manner so that the idea can be leveraged across a variety of different applications, not necessarily only when you have this square arrangement like what it is shown here. And so for that, we are going to look at the parity check matrix of this product code. See, this has 9 coded bits, and so this code word is C1 to C9. It's a vector 9 cross 1. And it introduces 5 parity bits. So H matrix has 5 rows. These 5 rows are essentially those 5 supervisory nodes. The first supervisory node is a check on the first 3 bits, C1, C2, C3. Right? This is the first supervisory node. It is a check of C1, C2, C3. Second supervisory node is a check of C4, C5, and C6. The third supervisory node is a check of C1, C4, and C7, and so on. And so that is what you see here. C1, C2, C3, C4, C5, C6, C1, C4, C7. So that is how we are building up the parity check matrix. And at the transmitter end, all of the supervisory nodes will always be 0, which is represented in this matrix format. And just like what we did for the Hamming code, we can draw the graph of this channel code. It has 5 supervisory nodes, and it has 9 what are known as bit nodes or variable nodes. And this is called a bipartite graph. The reason it's called bipartite is because it has, in total, it has 14 different graphical nodes. They get separated into 2 classes. That is why it's a 2-way partition of the nodes. And that's why the word bipartite came from. And the reason it is 2-way partition is because none of the supervisory nodes are interconnected. And none of the bit nodes are interconnected. Okay, so we will very quickly go over the message passing algorithm, and I'm not going to get into the details here, but I'll just show how the messages are getting exchanged. The variable nodes will get loaded with, in this case, I'm just looking at the hard decision decoding first. So the variable nodes will get loaded with whether the bit is 1 or erased. That's why it's called variable node. This initial values will be a variable. And now, instead of doing the row by row and column by column, we'll do message passing on this graph. By the way, this is exactly same as the example that we looked at for row by row and column by column. 5 bits are erased. First bit, second bit, fifth, and then the last 2 bits, which is the same eraser pattern that we had in that other example. So this is actually the same example as before, except now we are doing the decoding on a graph instead of on a square array. So the green means the messages are flowing upward, blue means the message is flowing downward. So in this iteration, 1 bit got unerased. Then in the second iteration, 1 more bit got unerased. Then yet another bit, and so on. Right? So this is how the message passing is working. Now a few points about the mathematical strength of this algorithm is that the complexity of the decoder, the computations that the decoder has to do, depends on the degrees of the check nodes and the variable nodes. So the degree is equal to the number of edges which are connected. And so here the degree is 3. Here also it is 3. Actually, all of these check nodes have degree of 3. And the variable nodes have degree of either 2, or even this variable node has a degree of only 1. The novelty of this algorithm is that each of the check nodes and each of the variable nodes don't have to do too much computation, because their computation will depend on how many bit nodes or variable nodes in one case, or how many check nodes are connected to it. Remember, those are the 2 formulas, the Gallagher's formula and that other product formula that we saw. And here in this case, because the number of edges or the degrees are pretty small, the computations that each node has to do is pretty small. Secondly, these computations can be parallelized, because each computation that each supervisory node does, it can do kind of independently. So what we can do is we can make the code word to be very, very long. Here we were looking at only 9-bit code word, but maybe we can make it to be a 10,000-bit long code word. Still, the computation will not grow tremendously, because individually each computation is going to be still the same as before. It's just that we'll be doing far many computations, because the number of variable nodes has become 10,000. And when we make number of variable nodes 10,000, if the rate of the code is 1/2, the number of supervisory nodes will be 5,000. So the check nodes and the variable nodes have become large, but at individual node, we are still doing the same computations. And furthermore, if we can parallelize the whole process, then actually we can do this type of computation. So that is the idea behind the low density parity check code. Okay, basically now instead of restricting ourselves to just the product codes, what we are going to say is that in general, we are going to consider this H matrices in a very specific manner. And what Gallagher did in 1960 is that he said that I'm going to come up with an H matrix which will have same number of ones in each row. So here it has 4 ones in each row, and so it's called the degree of variable node is 4. Sorry, degree of check node is 4, and each variable node is connected to 3 check nodes. So each of the columns have 3 ones, and so the degree of variable node is 3. DC and DV, or WC and WR. This is a 3-4 regular code. The reason it's called regular is because all the check nodes have the same degree of 4, all the variable nodes have the same degree of 3. But then the idea is that we do the same type of iterations. We can analyze the decoding probability and how it converges. Let us not look at it right now. There is something called density evolution method, which allows us to figure out up to what type of eraser probabilities this DV-DC 3-6 code will work. And that analysis shows that as much as 43% of the transmitted bits, or rather 42% of the transmitted bits can get erased, and the decoder will unerase it. If it is 0.43 and more, then the decoder will fail. But 0.42 is a pretty impressive number. If you are transmitting 100 bits, you are allowing 42 out of 100 to be erased. And no matter what eraser pattern it is, those 42 bits can get erased anywhere out of 100, and the decoder is guaranteed to recover those erasers. So this is the idea behind the mathematical analysis, which we haven't gone into. There is some formula that we need for deriving this. And then there is something called extrinsic information chart, exit chart, which is also pretty cool way of understanding when this iterative message passing algorithm will work or when it will fail. Basically, what they do is they draw these 2 curves. The blue is called the information transfer from the check node to the variable nodes, and the red is the information transfer from the variable to the check. And the idea is that the decoder will go through this tunnel between the red and the blue, and it will go through the tunnel in this staircase manner. The number of steps of the staircase is the number of iterations that the algorithm will take to converge. So in this case, it started with eraser probability of 0.35, and then after some maybe, I don't know, 7 or 8 iterations, the algorithm converged and the erasers became 0. And now if I make eraser probability to be higher, 0.4, then what happens is that the tunnel becomes narrower. And so this staircase becomes longer. The algorithm converges, but after maybe 20 iterations. I haven't shown that here, but if I make this p equal to 0.43, then this tunnel will close. This red and the blue will touch each other, which shows that the staircase cannot be built. It doesn't have a passage through 0, which means that the algorithm will not converge. So that is the idea behind extrinsic information transfer chart. We will not look at it today, but instead I want to look at a paper written by some person, Bernard Leonard, So he has actually done a very good job. Maybe he wrote this as his student project paper, but he has done a very good job of defining these LDPC codes, the variable nodes and the check nodes for this type of H matrix. He has described the hard decision decoding scheme, and that hard decision decoding is very similar to what we were looking at in terms of the product codes, in terms of the graph. Basically, first how each check node receives messages and what type of messages it will send, and then how each variable node receives messages and what type of messages it will send. The idea is that in the hard decision decoding, okay, let me ask you this. What will be their algorithm at the check node? In the hard decision decoding, the check node will simply do what?
Some majority based selection.
No, check node is an SPC code.
Oh.
So it will just do just the modulo 2 sum. Whereas variable will do majority voting. So that is what is done here. For soft decision decoding, it's exactly the same structure where all the variable nodes will pass their probabilities to the check node. And check node at a time will take n-1 such probabilities, and using that it will compute the probability that it will send to the remaining variable node. And it will do that one by one. First it will go to this variable node, and that time it will take probabilities from these 3 variable nodes and it will send a down arrow here. Then it will do a down arrow here. Then we'll do the down arrow here, which is shown here in this diagram. And same way, at a variable node, remember, we have probability coming from the demodulator also. So that is this y of I. And we have probabilities coming from the check nodes, which are this denoted as Q values. And so a variable node will take n-1 Q values coming from the check nodes. It will take y of I, and then using that it will send a message back to the check node. What are the messages that are being sent? Check nodes send the messages according to this formula. Remember, this is the formula that we have looked at earlier, the Gallagher's formula. What is the formula that the variable nodes will use? It is this product formula that also we have seen earlier. And this K is just the Bayesian multiplier term, which makes the summation of 0 and 1 to be equal to 1. And this P of I is one additional part which is coming because of this Y of I. Y of I is the value coming from the demodulator. And probability that Y of I is 1 is P of I. And so that's why we do one additional multiplication with P of I and 1 minus P of I. So that is it. There you have it. That is the essence of message passing. Once you can do this, then you just repeat it on all the check nodes and all the variable nodes, and then you just keep on iterating the way we did it for the product codes. Okay, so we will stop here.